Find a formula for the n terms of the sequence 1, -1, 1, -1, 1. This is what is known as an alternating sequence because it's alternating in the sign. And for alternating sequence, the expression that will determine the sign is -1 to the n power. However, we usually want n to start with 1. If we were to use this, then when n equals 1, we have -1 to the n, which is -1 to the 1 power, which is still -1. But we want the first term to be positive, so we would need to update this. Instead of using the power 1, we would want to lower the power by 1, which is n minus 1 instead. And so when n equals 1, we now have -1 raised to the 1 power, and then minus 1. But 1 minus 1 is 0, and -1 raised to the 0 power is positive 1. When n equals 2, -1, n is now 2, and then we have minus 1, which is -1 raised to the 1 power, which is -1. So the second term is -1. And so we know for sure that the nth term is a sub n equals -1 raised to the n minus 1. Note that if we use n plus 1, it will work in this case as well. And this formula is not unique, but as long as it works, as long as it represents this sequence, then we can use it. And again, we can use any other formulas that satisfy this sequence. We know that this works because when we plug in n equals 1, we have positive 1. When we plug in n equals 2, we have -1, and so on. Always check to see if the formula that we come up with works. And again, when n equals 1, a sub 1 is -1 raised to the 1 minus 1, because n is now 1. And so we have -1 raised to the 0 power, which is positive 1. A sub 2 is -1 raised to the 2 minus 1. The minus 1 is fixed. So this is -1 raised to the 1 power, which is -1. A sub 3 is -1 raised to the 3rd power minus 1. 3 minus 1 is positive 2, but -1 raised to an even power is even. Power will give us a positive. And so this is now positive 1. Again, always check the terms to see if the formula that we come up with works. For the second sequence, a sub 1 equals 2, a sub 2 equals 6, a sub 3 equals 10, a sub 4 equals 14, a sub 5 equals 18, and so on. The n formula is simply a function that would represent these with the domain. When n equals 1, we need to have f of 1 equal 2. When n equals 2, we need to have f of 2 equals 6. When n equals 3, we need to have f of 3 equals 10, and so on. When n equals 4, f of 4 has to be 14. And so to come up with the formula, we need to see if there is an apparent pattern here. Notice that the output is increased by 4 each time we increase the input by 1. N go from 1 to 2, that was the input. We would increase the output by 4. From n equals 2 to n equals 3, the input increased by 1, but the output increased by 4. And so every time an output increase by the same constant, then we know that this is a linear function, and that same constant is the slope. If it is linear, Then we're looking for the equation of the form y equals mx plus b, where m is the slope. The slope is the constant rate of change, and we know that the slope is 4. And so y equals 4x plus b. To find b, we just simply use any point. It is convenient to use the first point when n equals 1, f of 1 equals 2, or the input is 1, the output is 2. So this is 2 equals 4 times 1 plus b. 2 equals 4 plus b. So b equals 2 minus 4, which is negative 2. The equation we're looking for is y equals 4x minus 2. But there's no x in this formula. This is sequence, so we need to use n for the input. And so f of n equals 4 times n minus 2. The n term formula we're looking for is a sub n equals 4n minus 2. As always, we need to double check this. A sub 1 is 4 times 1 minus 2, which is 2. The first term is 2. When n equals 2, a sub 2 equals 4 times 2 minus 2, which is 8 minus 2, 6. A sub 3 equals 4 times 3 minus 2, which is 12 minus 2, 10, and so on. And we see that, yes, this is 2, 6, 10, and so on. Lastly, the sequence 1, 3, 4, 5, 9, 7, 16, 9 over 25. Sometimes we would need to stop and observe any apparent pattern. Observe that in the denominator we have 4, 9, 16, 25. These are the perfect squares. 2 squared is 4, 3 squared is 9. 4 squared is 16, and 5 squared is 25. And so we want the denominator to have perfect squares, so we would rewrite this one as 1 over 1, because 1 over 1 is 1. 3, 4, 5, 9, 7 over 16, and 9 over 25, and so on. In the numerator alone, we would have the sequence 1, 3, 5, 7, 9, and so on. In the denominators alone, we would have 1, 4, 9, 16, 25. In the numerator, we see that the outputs are increased by 2 each time. And so we must have the sequence in the numerator only being 2n plus minus 1. We can use the input n equals 1, the output 1, the input 2, the output 3, the input 3, the output 5, and we can find the slope m equal 2. And then once we found the slope, we have y equal 2x plus b, and then if we plugged in x equals 1, y equals 1, then we have b equals negative 1. And so the numerator is 2n minus 1. The sequence starts with n equals 1. And so this is a sub 1, not a sub 0. The denominators are basically the squared of the input. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And so we see that in the denominator, it is simply n squared. When n equals 1, we have 1 squared. When n equals 2, we have 2 squared. Putting these together, we must have a sub n equals 2n minus 1 in the numerator and n squared in the denominator. But we still need to check. A sub 1 equals, if we plug 1 into n, 2 times 1 is 2, 2 minus 1 is 1, and in the denominator 1 squared, and so we have 1. The first term is 1. A sub 2 is 2 times 2 minus 1 over 2 squared, which is 3 over 4. A sub 3 is 2 times 3 minus 1 over 3 squared, which is 6 minus 1 is 5. In the denominator, 3 squared is 9. And if we keep checking, we see that, yes, this formula satisfies the given sequence.